Okay, thank you. Thank you very much for the introduction and for the invitation to speak here. It's a pleasure. Long time ago I studied here, but really long time ago. So let me start with the plan of my talk. So it will have three parts. In the first, I will briefly say something about stable embeddedness. And definable types. So the connection to the title of the conference is definable types, definability. But also in the third part, we will see theories that are decidable, so there's a little bit of computable aspects as well. So the second part, I will talk about beautiful pairs. So this is joint work with Pablo Cubides Kovacsics and Jinhe some time ago. And then in the third, it's ongoing work joined with Udi Hrushovski and Ting-Chang Zhou, who is here, and Jinhe as well. And this is let's enter non-standard Frobenius. So let's start. So stable embeddedness. Let me define what it means. I'll give it a slightly unusual definition. So let M be a structure, A is N an elementary extension, but A can be some intermediate set. So between M and N, and say L structures, elementary extension of L structures. Now let me say that M is stable embedded. Stable embedded, I will abbreviate it as E in A if the trace of every A definable set in N with M is M definable. So if for every formula with parameters from A, say in I don't know, N variables maybe, you can look at the set it defines in N, so the set of tuples, maybe not A, maybe B, in M to the N, such that N can, because N can evaluate it, A is it from N, so N says phi of B bar is actually, but this is, what is this? This is a set the formula defines in N, but then you cut it down with the smaller structure. And this, if this is L of M definable. So the trace of a definable set, well, with parameters from A, is definable in the small structure. Okay. Let's look at examples. Examples. 1. T is stable if and only if for all M in N, models of T, M is stable embedded in N. Well, this is, well, one version, I mean, by one of the main theorems from stability theory, types are definable. Okay? So a theory is stable if and only if this always happens. 2, T O minimal. Now, if you have an elementary extension of models of T, then there is one obvious condition. Look, for example, the dense linear order Q is not stably embedded in the dense linear order R because you have the Dedekind cuts. So certainly, by ominimality, there cannot be Dedekind cuts. So there's a necessary condition, but actually is stably embedded. So M is stably embedded in N if and only if M is Dedekind complete in N. This is Marker-Steinhorn. So it means it's enough to check N equal to 1. If you have it for definable sets in one variable, then you have it. Yeah, so this is Marker-Steinhorn. For example, whatever O-minimal structure you put on the reals, it will always be stably embedded everywhere. Okay. Our third example from valued fields. QP is stably embedded in every elementary extension. Now I want to do a spoiler so that you can think a little bit later it will come. Why? What is the value group? Pressburger, it's the prime model of Pressburger arithmetic, and Z is the only model of Pressburger arithmetic which is stably embedded everywhere. Check, exercise. And it's also maximal valued field, and we will see later that this is exactly what we need for this. Okay. Anyway, so these are 3 examples. Now, a fact, there is a duality, which is completely trivial, but it's good to. So duality between stable embeddedness versus definability of types. So let's express this. So in the above context, so the following are equivalent for M in A in N. M is stably embedded in A, if and only if every finite tuple you can take from elements of A has a definable type over M. So for every tuple A bar from A, finite, the type of A over M is definable. Now let me define it for those who don't know what this means. This means for every L formula, phi of x, y, so tuples, x is the length of A, y bar is the parameter tuple length. There is an L of M formula, so I'm allowed to use parameters from M. dp, it's usually called defining scheme for p of phi, in the parameter variables, such that the following holds for b in m to the y, so you can plug it in as a parameter. The instance of the formula is in the type if and only if, so this is p, sorry, p is this type, p of x, this type of A over M, is in if and only if this formula dp phi holds. So the decision whether you go into the type, the instance goes into the type or not, is a definable one, not just an arbitrary. Okay? So this is completely trivial, that this is equivalent. You just change the role of x and y, so to say, in your head. Okay, so now I need another group of examples, which I already gave you as an exercise. So let's look at valued fields. So recall a valued field is a field, okay, endowed with a valuation with a map V from K it goes to gamma union infinity, say surject if I want, such that gamma is an ordered abelian group, such that 3 conditions hold. It's a little bit like a norm. So the valuation of x is 0 is infinity if and only if x is 0. 2, it is a group homomorphism. So v of x times y is v of x plus v of y. And finally, you have a strong triangular inequality. The valuation of the sum is bigger or equal to the minimum of the valuation of x, valuation of y. Yes? Sorry? Plus, yeah. Thank you. Okay, so these are the axioms of evaluation. For example, p-adic valuation on the rationals, or t-adic valuation on rational function fields, and so on. So now, some objects are here. So gamma, k, gamma is called the value group. And you have the ring of integers, so OK, the set of elements in K of valuation bigger or equal to 0 is a subring, it's a local ring, and its unique maximal ideal is the set of elements of strictly positive valuation. And then you can, it's unique maximal ideal, you can form the quotient, and so little kk is OK mod mk is called the residue field. And the whole bunch of the model theory of valued fields for Henselian, say equicharacteristic 0, is that we understand the valued field from value group and residue field. And that will also be the case for this theme and for this talk today. Okay. So I need a last definition, and then I can I can then characterize definability or stable embeddedness for valued fields. So an extension of valued fields say L over K is called separated. This is a notion due to Bauer. If every finite dimensional sub K vector space of L, V of L, has a nice basis. So admits a basis, it's called evaluation basis, a basis B1, say up to Bm, such that you can compute the valuation of a K-linear combination by looking at the just at the coordinates, so to say. It's always the minimum of the valuation of alpha I bi. Okay, so this is called separated. But don't need to jump because I grew, yeah, grew a bit taller. So. Okay, good. So now a characterization of stable embeddedness for valued fields. So this, we state it as a fact. So for algebraically closed valued fields, it is due to Cubides Kovacsics and Delon. A more general context due to Pierre Touchard and also in other contexts, other people. So for an elementary pair, of models of, and now I have a certain number of theories of valued fields, ACVF. So this is a theory of algebraically closed, non-trivially valued fields. You can choose the language that you like. For example, you name the ring of integers as a unary predicate, or there are other possibilities. You work in three sorts with a sort for the value group and the residue field. I will not make this precise here. So algebraically closed, non-trivially valued field, separably closed, non-trivially valued fields, Henselian fields of equicharacteristic 0. So Henselianity is a replacement for completeness, which can be expressed in first order. Equicharacteristic 0 means that the residue field is also of characteristic 0, not just a full field. And also the theory of the p-adics, the periodically closed fields, and theories of finite extensions. For all of these, one has, okay, the following are equivalent. What we are interested in is when is K stable embedded in L? Well, three things. L over K is separated. And now comes the Ax-Kochen-Ershov principle. Gamma K is stably embedded in gamma L as ordered abelian groups. And the third bit, the residue field is stably embedded in the larger residue field as fields. So in the ring language. Oops. Okay, good. So that is for these theories, there's a complete answer of when you have stable embeddedness. Okay.
So point one, you mean as valued fields?
As valued fields, exactly. That is important. As valued fields. And you choose your language because it doesn't matter. This is it's as long as you don't add definable sets, it will have the same answer. So in every language you can. Okay. So you completely understand what's going on here as when it comes to definability. Now, let me give examples before we continue the second part. So now look, you can take any algebraically closed, let's look at examples of ACVF. Any algebraically closed field, and now you take the valued field, which is the Hahn series field with coefficients from the reals. This is a maximal field. It does not have any immediate extension. Every extension of it is separated. The value group is the reals. So we have just seen by Marcus Steinhorn that the reals are stably embedded everywhere, and the residue field is stable, but we have seen every stable thing is stably embedded everywhere. Okay, Second example, so this is for ACVF, so is stably embedded everywhere. Same is true for R. So now let's do real closed valued fields with complex valuation. So twice the same reason, yeah? Residue field, real closed field, okay, value group, the reals, and also maximal, yeah, is stably embedded everywhere. And also the periodics, as I said. Right, but even K over QP finite extension, then K is stably embedded everywhere. Okay, good. So that is a characterization somehow in this context. Now let's move on. So these are, this phenomenon of stable embeddedness / definability of types is what I'm interested in, and mainly for valued fields. Okay, so second, now I think I will not write it, I will just say it. Sometimes I should not write. So if you do geometry, for example, if you do algebraic geometry, you can look at the Weyl type, the naive approach, and just look at as a variety as a set of points. But you can also say, instead of looking at V and affine variety over K, I can go to a stack of the ring of regular functions and look, so all the prime ideals of this ring. But what does this correspond to? This corresponds to the type space as a type space in algebraically closed fields. Because by quantified elimination, a type and the prime ideal is the same. So this is something you can do, but you can think of this move to somehow adding more points, like virtual points, when you go from the variety to the scheme associated to it. You can think of it as a move to a set of definable types. No, now there's another one. If V is an algebraic variety defined over a valued field, and Hrushovski-Leuzer, they associated to it the stable completion V hat, which is the set of definable types on V that are orthogonal to the value group. That means if you realize them, you don't add any values. So relatively to the world you are, you don't add values. And this is a model theoretic analog of the Berkovich analytification, but you can define it for every valued field, not just for complete with Archimedean value group. Okay, so, and these have been used a lot. So this is in the background. That's why we were interested in this project, is because of this use in non-Archimedean geometry. And the fact is, in both cases, so in the first case, this type space in algebraically closed fields. In the second, this space of definable types orthogonal to the value group. These spaces of definable types, because all types are definable, they are stable. These spaces of definable types are strict pro-definable, or have a strict pro-definable structure. Pro-definable is clear. It's a pro-object in the category of definable sets, so you have maps between definable sets. Strict means, one version, you can present it in a way that the transition functions are surjective. Or the projection of the projective limit to any of the coordinates or any finite product of coordinates is definable and not just type definable. Okay, good. Now, how does one prove such a thing? Well, we came up with a semantic approach. So, semantic approach to strict pro-definability of spaces of definable types. Okay, so we make definable types into structures. So how do we do this? Okay, so we work in the language of pairs. So if L is my original language, let's say LP, you add a unary predicate. So now I can single out a subset. and I say CDEF is the class of structures, of LP structures, of the form A, P of A, such that, as before, P of A is my M, and this is maybe my N. I work in some background theory T, but I want that the predicate is an elementary substructure. I don't want that A can be anything, it's in between, like in my definition of stable embeddedness. A is something, and such that P of A is stably embedded in A. So dually, every finite tuple from A has a definable type over P of A. So I made it into structures, that's all I did. The situation is before. Now, what are the morphisms? So, yeah, so if I have two like this, so A P of A, when does it lie nicely? And let me index nicely by BP. Well, first of all, I want it to be an LP embedding. I should say something. I forgot to say at the very beginning here, T complete with quantified elimination to be on the safe side. Yeah, I want to fix the theory T complete and quantified elimination. Sorry. So now, what do I want? Well, it's an LP embedding. So it respects the predicate. That means the predicate P of B intersected A is P of A. But I also want that the type, A goes into B, so I can look at the type of the L type in the original language of A over the larger set in the predicate. I want that it's a canonical extension of its restriction to A. The canonical extension of type of A over P of A. So what does it mean, canonical? It is a definable type. So it has a definable scheme. You have all these formulas dp phi, and I want that the same formulas describe the larger thing. It's the freest possible extension. For example, in algebraic closed fields, if A bar is the generic of the variety V over P of A, it should also still be the generic of the same variety over the larger set. And this makes sense because the types are definable. There is a unique extension which is canonical. And so these are good embeddings in my category. Okay. Other questions for this setup? I insist, the larger one can be anything. It lives inside a model of T, but since I don't control whether I can go to a model, I just take arbitrary sub-things. Questions? It could be, you can take it to be a substructure if you want. Yeah, it's maybe safe, or work in a relational language. Okay. But for the purpose of this talk, let's say A is a substructure. It doesn't harm, yeah? Yeah. I can make it relational, and then I never need it. Yeah, it doesn't. Okay, good. Now, fact. This is somehow the general fact why the machinery works. So this makes the machinery work. Assume this category has the amalgamation property. That means when you have a little one, the left and the right, then you can combine to a third one. Then I can, of course, construct, like Freistil limits, I can construct rich structure. So what is it? There exists a beautiful pair, we call it, of T, i.e. some structure in this formalism. So the little one is a model, the large one sits inside a model, such that for all A dp in B from this category and F from a BP embedding into M, assuming B is small, at most the cardinality of the language, I can extend the embedding to an embedding of P. F tilde B also BP into M. So it's rich, yeah, if you have like a typical, like in Freise amalgamation, the typical diagram. The only thing is I want B to be small, namely at most cardinality of the language, and I want to with morphisms that are only using, I mean, all of this shape. Yeah? Like respecting the defining scheme. And if I have amalgamation, of course I can do it. This is a little exercise. Okay, so they exist. Second of all, we have had a lot of talks about back and forth. Any two are back and forth equivalent just by definition. Yeah? So any two beautiful pairs are back and forth equivalent. In particular, elementarily equivalent. So set TBP, their common theory. It's a complete theory, yeah? Complete. LP, yeah? Theory in LP, in this new language. So I have a complete theory of beautiful pairs. Good. And somehow this encodes everything I need to ever know about definable types in T. So it's just, I mean, pairs are, of course, nice tools since the beginning of model theory. And here they also are used. So let me just give you two further definitions. We say this CDEF has the extension property if whenever you have a model of this theory of your beautiful pair, I mean a model of the theory of beautiful pairs, then M is also a model. This has a characterization in terms of an extension property, which is like a Tarski-Wood property. You can guarantee on the way a Tarski-Wood property that makes the limit be a model of T. I don't want to write it. I mean, it's an exercise how to write this. More importantly, CDEF has, and now I'm not very proud of this terminology, but it is used by us, has beauty transfer. Beauty transfer if the beauty transfers to saturated models. So if there is, or equivalently all, an L plus saturated model of TBP, which is a beautiful pair. I mean, as always in model theory, you can do whatever you want, but if you cannot have a saturated model with the good properties, then you didn't do anything and you don't understand the types. But if you do, then it's good. Then somehow you control the types. And so this we call beauty transfer. Okay, so this is the setup. So why is it interesting? Well, there's a general theorem I want to state now. Actually, this is the machinery that just gives us strict pro-definability. For example, we get the Hrushovski result cheaply back and not by hand. So let me continue with this. So here's the theorem, which once you have the setup is not difficult. So it was already on Archive 2021. We hope that it is accepted in a couple of weeks. Okay. Assume CDEF has the amalgamation property and beauty transfer. So saturated models of the theory, which I now know it exists, yeah, are beautiful. Then, for every definable set D in some model of T, the set of definable types on D, yeah? Definable set D. The set of definable types living on D is strict pro-definable. So somehow the sorry? Over U. So if this is, yeah, if D is over the same set of parameters actually. If this is over A, this is over A. Yes, same set of parameters. It's a canonical object. I mean, the coding is so canonical that you can do. Okay. So this is somehow why we did all this formalism, but now let me give examples. So there is, of course, so the following theories are very good, have the amalgamation property, also the extension property, but it's really not essential, and beauty transfer. So you can tell me the first example, maybe, by history, 80s, from the 80s. Poizat. Stable NFCP. I mean, Poizat showed for a stable theory it is NFCP precisely when this formalism works. The formalism is simple in a stable theory. T-stable NFCP. It's actually if and only if, but okay. Beauty transfer if and only if. First. Second, TO minimal dense. Check, always. So for example, RNX, this is actually Anand Pillay has a first paper, but then there is by Zalov-Poizat who show, there is a hypothesis by Zalov, and by Zalov-Poizat show that actually it always works. They don't phrase it like this, but we see that the theories constructed in these papers are exactly, and also what falls into this is the tame pairs of real closed fields studied by Lau and Levenberg, for example, and more generally. But this is somehow it always works. So, yeah. The third one, let me do examples here. I didn't give examples for the first one. For ACF, say,
dense, you mean
dense, no. O minimal dense. T is O minimal dense, period. T is O minimal dense. So that the underlying order is dense. Not every O minimal theory has maybe a dense underlying linear order.
So then what is the tame business?
The tame business is you have to be stably embedded, of course. So tame pairs, I said that, you only look at definable types, so you'd better go to elementary pairs that are, the small one is Dedekind complete in the large one. And there is a generic object, so to say, which, for example, for real closed fields is just proper pairs. Difficult theorem, not easy, at least, yeah. But for any O minimal theory, Anand provides an axiomatization, which is consistent providing something, and then by Zalov-Poizat showed you can always do it. Okay? So this is old. It's just we put it in this context. An example is if you have T the theory of algebraically closed fields of some fixed characteristic, then TBP is just proper pairs. It's just proper pairs. This is by Abraham Robinson. It's already a complete theory. So nothing further. Just proper pairs of algebraically closed fields are already beautiful pairs. Theory of beautiful pairs. Or minimal dense. Yeah, so let me give an example. Not real closed fields. This is closed fields also, but for me it's proper tame pairs of RCF. Is RCF BP? Or tame pairs, yeah, automatically proper. And then in DOAG, what is DOAG? BP. So divisible order abelian groups. So now, if you have a pair, then you are a model if and only if. We already know Markov Steinhorn, so we know the small one is Dedekind complete in the large one. So M Dedekind complete in N, of course. But then I have two things. I have to realize the infinitesimals and the infinite elements, such that N contains both infinite with respect to the predicate and infinitesimal elements. Note, in real closed fields, it's the same because you have a pole, yeah? You can, of course, send 1 over x. You go from 0 plus to plus infinity. This is not possible in DOAG. So you need to fill both. If you fill both, it's OK. That's already a complete theory. OK. Good. Now, I want to do, so the motivating example was ACVF. So let's work in ACVF. So tier completion of ACVF. We know in order to complete this, we only need to specify the characteristics of the field and of the residue field. Could be 0, 0, 0p or pp. Okay. Then, such a structure is beautiful. A is a model of the theory of beautiful pairs, if and only if. We already know, okay. P of k is an elementary substructure of k, and k over p of k, we know it must be separated. because we know else it cannot be a definable, a stably embedded extension. The second is the residue field is, but it's always okay. So I only need to say that the residue field pair, P of K, I only need a proper pair, in other words, ACF, BP. So just a proper pair of algebraically closed fields. Value group, the same, a beautiful pair of doacs. Which means what I said, yeah? You fill the cut at 0 plus, you fill the cut at infinity. Okay? It's not well written. You're absolutely right. It should be NM. You're absolutely right. Let me write it as before. MP of M, not to confuse anyone. P of M is Dedekind complete in M, such that M contains both infinite and infinitesimal elements with respect to P of M. That's what I meant. Sorry. Thank you. Okay, questions? So, but this is a pattern, and we can do Ax-Kochen-Ershov on this thing. So RCVF, actually this is in our paper. And now 4 is also from the same paper. So RCVF, actually similar to 3. You see what you have to do, yeah? The residue field must be a beautiful, the tame pair in the sense of closed fields. Value group is the same, separated. That's it. And yeah. So RCVF is similar to 3, but actually there is an Ax-Kochen-Ershov theorem for beauty, principle for beauty. I don't write it, but you can imagine what it is. Assume the residue field is okay, so it has AP, EP, beauty transfer. The value group is okay, it has AP, EP, beauty transfer. Then the value group also has it, and the axioms look exactly the same. So for Hils 0, 0. Separated, value group is beautiful, residue field is beautiful. So it's very simple. Okay. So in this way you get C of double brackets T, R of double brackets T, I don't know, many examples. Yeah. Okay. Last example, yeah, also ACVF, it's a bit different because you have to work with separability, any degree of imperfection. Also infinity is okay. This is by myself and a former master student. We proved this, okay. So that is maybe let me mention some variants. So this all can be relativized. Not surprisingly, take your favorite subclass of definable types. So don't take the whole CDEF, take subclass. For example, orthogonal to gamma. Or bounded definable types in ACVF, so those that correspond to Huber analytification. So for bounded definable types, what changes? Everything is the same. In the axioms, you just say, I feel the cut at 0 plus, but I don't feel the cut at plus infinity.
What is bounded?
Bounded means when you're in a valued field, you realize it, and you cannot get a rational function. If you evaluate it on it, you get an element at plus infinity in the value group. They're bounded in the value group. Okay? Whenever you have you have a type, take a rational function. So DCL intersected gamma, you cannot go to plus infinity. That's bounded. So it means orthogonal to the type at plus infinity in gamma. That's what bounded means, okay? You're orthogonal to plus infinity. You cannot go with the definable function to plus infinity, or so that corresponds to Huber analytification. I mean, a model theoretic version of it. We can also do the Hrushovski one. So for definable types, orthogonal to the full gamma. That means orthogonal to plus infinity and also orthogonal to 0 plus, and then you don't get anyone new in the value group. And then we get the strict pro-definability of these spaces back. So that finishes my second part. Now this was a bit old. This is already around for 3-4 years. Now in the last 15 minutes, I want to talk about the new project with Tingshang, Vince, and Udi. But maybe if there are questions, you should ask them now, because I might need to wipe at some point. Okay, so part 3. But now let me maybe do the following. Now look, we have a couple of places where we can enter the Frobenius. We have ACF, maybe ACFP. P is a prime. We also have ACFP, beautiful pairs. That just means proper pairs of ACFP. So an algebraically closed field of characteristic P sitting inside properly an algebraically closed field of characteristic P. But we also have ACVF PP. So algebraically closed valued fields of characteristic P. And we also have by the above ACVF PP. Okay, it's a lot of indices. BP, lots of P's. So we know what it means. Yeah? So we have axioms. And this is clear. This is proper pairs. This is non-trivial algebraically closed. Non-trivial valued algebraically closed. And this just means here, yeah, a proper pair. Separated value group is, say, a tame pair of Doak. Residue field is a proper pair of algebraically closed fields. Okay? And now I take models of each of these and I add a Frobenius. So and then I let 10 p to infinity. So let Kp, or actually, P is a set of primes. And Q, set of prime powers. Okay? So for Q, P to the n from Q, let. And now I give you structures in these. So Kp is K, so Kq, is K Frobenius Q. X goes to x to the q. This is a difference field. This corresponds to this one. LQ, okay, where K is an algebraically closed field of characteristic P. LQ is L Frobenius Q, where L is a proper pair, so it's an ACFP beautiful pair. M comes here, and then comes N, yeah? NQ is N Frobenius Q, MQ is M Frobenius Q, where M is a model of ACVF PP. And finally, N is the most complicated. NQ is N Frob Q, where N is a model of beautiful pairs. So ACVF PP, PP. Yeah. So what I do, of course, for all of these structures, the Frobenius is an automorphism. So these are now structures endowed with an automorphism. This automorphism for Q fixed is definable, so nothing is added to the structure. But of course, if I take alpha products, this drastically changes. So, so let L sigma is the ring language together with a symbol for a unary function. So a difference field is K sigma, where K is a field, and sigma is an automorphism of K. So we're interested in difference fields, at least, yeah, because I have a difference field, I have a valued difference field, I have a pair of difference fields, and then I have a pair of valued difference fields. Okay, but let's start with the simplest is the most complicated. So because here the non-standard Frobenius result enters, so Hrushovski, there is now other proofs by geometers. Sorry, I forgot something. So there is a theory, ACFA. So recognized early on by Angus, Lau, and others. The ACFA, the theory of existentially closed difference fields. So there's a model companion, and let denote ACFA its theory. It is a very well studied theory, very nice, has geometric axioms. I don't want to give the axioms at all because I don't have time, but this is something well studied. And so here is a fact, which is a big theorem. 1, Hrushovski. So ACFA is nothing but the limit theory. Those the sets such that KQ satisfies phi for Q large enough from Q. And if I go to characteristic 0, let me just indicate characteristic 0 like this, then it's the limit theory of all prime. This is very deep. It's true. Okay, it follows decidability, for example. Okay. Now, the valued category. So we are on the left, yeah. This was on the left upper corner. Now we go to the left lower corner. This is also known. What happens when you let tend Q to infinity? So the lower one, so there is a theory, VFA, of valued difference fields, explicitly axiomatized such that it is the limit theory of the LQs. In characteristic, you note you have two regimes. It could be characteristic P, and the n goes to infinity, P to the n. This is difficult, so this is Hrushovski for characteristic P. For characteristic 0, it was done by a student of Laus, or can be inferred from the work by from Salish. VFA 0, if you restrict to primes, so you automatically get characteristic 0 in the limit. So this is Sturhan, published under the name of Asgin. It follows from his work. What is the axioms? I will not write them down. The axioms of VFA 0. You have to, I mean, it's the residue field is an ACFA 0. That's by 1. Because the Frobenius acts on the residue field in the same way. So if I have 1, I also have the residue field is a model of ACFA 0. The valuation is infinitely fast increasing because Frobenius acts by multiplication by P on the value group. So if P goes to infinity, it must go to another Archimedean class. So if X is larger than 0 in the value group, sigma of X is larger than n times X for every n. Second axiom. Third axiom, some kind of Henselianity, sigma Henselianity. Fourth axiom, the value group is divisible as a Q of sigma vector space. So if you have sigma which sends people to at infinity, this gives you an order. Sigma is ordered at plus infinity. You have an ordered field. Now you have a vector space given by the action of sigma, and you want that it's a divisible thing. So you want that it's a vector space over Q of sigma. That's a complete axiomatization of VFA 0. Okay. So that is in the background. And now the new, so this is old, yeah? Left-hand side is known, sometimes difficult. And now we do the right-hand side. So in the last 5 minutes, we can just complete the right-hand side. Yes, so let me wipe. Let's see, eraser here. So that's what I said in my abstract. We get surprisingly simple axioms for the limits of the pairs as well in Frobenius, because we can identify them with beautiful pairs. I mean, the relationship has to be given. So to finish, yeah, time is okay. So this is the new work. So effect, first effect. So this is Hrushovski. In a paper from 2004 where they study endomorphism, this is a paper people do not read, but one should read it actually. They prove that, okay, let ACFA TP, T for transformal, be the theory of proper pairs, the theory of proper pairs, LK of models of ACFA, such that the small one is transformally algebraically closed in L. That I mean, you can be sigma algebraic and still it defines an infinite set. For example, the fixed field is infinite. For example, the fixed field doesn't grow. But everybody from L, but not from K, does not satisfy any equation with any sigma equation. Yeah? Even x sigma of x, sigma square of x, and they're all algebraically independent. Okay, good. So actually, if then okay, any LK model of ACFA TP, then K is SE, is stable embedded in L. That means all these types are definable. This is in their paper, even in characteristic P. Even in characteristic P. So, of course, the fixed field is a pseudo-finite field. There are many. There is random phenomena. You don't get all types defined. Actually, it's difficult to find one non-realized type which is definable. We found one, but it's not easy. But okay, so this is by Hrushovski. But now look, if we do, so now the theorem. Distinction in the room and others. So we show that actually taking the limits is also nice. So ACFA TP is already the limit theory. So for Q large enough, there is nothing more you can say. Look, it's clear that in the limit it will be transformally algebraically closed. You can check. I mean, locally you're just algebraically closed, but then Frobenius is turned into sigma, and you would have a problem if not. So this is a limit theory. And in characteristic 0, it works as well. As before. Now, life would be too good, so we cannot do. This is the first part, sorry. Second part. Let T be a completion of ACFA. You have to fix the characteristic, but you also have to fix the action of sigma on the algebraic closure. That is a complete invariant up to isomorphism. Then T union this ACFA TP is the theory of beautiful pairs for definable types, but they're all definable by the fact orthogonal to finite rank. Or sigma algebraic, let me say this. So if you're orthogonal to those, that means even in the algebraic closure, there's no one which was not in K but sigma algebraic. So it has extension property, amalgamation property, and beauty transfer. So it means we can recognize this limit again as a theory of beautiful pairs with the good properties now for difference fields. So if you are interested in coding in a strict pro-definable set, the class of all definable types living on a definable set, where you know that they're orthogonal to finite dimension, then you can do it in a strict pro-definable way. And then the final one is a little bit less nice, I think, because we were lazy also. I mean, I don't know. We want to do characteristic P as well, but we are not able to do it yet, because the result by Hrushovski is significantly harder than the characteristic 0 result. So let me only state what we have. So VFA 0 TP is defined as you imagine. What does it mean? Separated pairs. Residue field is a TP. Value group is a beautiful pair of this O minimal Q of sigma ordered vector space I have in VFA. And the residue, I already said. And an elementary pair of models of VFA 0. Yeah, so using separated plus Ax-Kochen-Ershov axiomatization. Okay. Good. And then completions are obtained completing the ACVF on the residue field. That's all you need to say. Once you fixed the completion of the residue field, you fix the completion of the residue field pair by this 2 here. And then by the machinery, you fix the completion because you have the theory of beautiful pairs or something. And finally, we also have this limit result. For P, so only characteristic 0. So you know precisely what happens even in these. So I mean, we hope, initially we wanted to say, okay, now we can study dynamics on Berkovich spaces with model theoretic eyes because we know what But we are not able to do this, yeah? I mean, at the moment. But at least we know what limit of Frobenius does on these Hrushovski reserve spaces. Well, kind of, not completely. But we can construct the analog of what they do in the category with Frobenius. And get something definable. Okay, I think I'll stop here. Thank you.